So today we're going to introduce the concept of electric power. Now, what was power when you learned it in the context of just mechanics? Work over time, right? The rate of work. That better? And what was the unit for power? Yes. What is the unit for power? Now, the same holds true. Oh, and by the way, what is work equivalent to?
No, because that's force. Force over time, volt over time.
Think bigger picture,
Force.
which means work is equivalent to energy. Energy and work are interchangeable, right? When I do work, I change the object's energy.
What is that?
Okay. Now, why do I write it that way? Because a lot of times we'll rearrange it then and say that the energy is equal to the power times time. Right? So,
Wait, that means what? Oh, okay, never mind.
because a watt is a joule per second, right? And so if I do joules per second times seconds, I get joules. Now,
So the W on the left side is work or watts?
work, because it's the symbol in the equation. Remember, don't get symbols and units confused. Symbols are in equations or relationships. Units are attached to numbers. All right? Okay. So, in electric power, we have this relationship. Because what is the definition of current? Right, it's the rate of change of charge. So it's coulombs over seconds. And a volt is defined as a
Coulomb.
joule per coulomb.
Wait, so then...
Oh wait, I didn't do that? Okay, that's more for next year anyways. And so the coulombs cancel and I get joules per second, which is power. It's a watt. Alright, so now, let me make my general disclaimer before we go on. As I've said many times, we keep things simple this year. I'm going to ask questions like, what's the power rating of a certain light bulb? Or I'm going to tell you that the power of a bulb is blank. When I say that, I mean when it's in a circuit like it's intended to be. In other words, if I have a 60 watt bulb, it's going to give off energy at a rate of 60 watts so long as it's plugged in to 120 volt alternating current circuit. If I change the current or the voltage, then I will get a different power other than what it actually says it is. Right? So that's just my disclaimer, because next year we're going to have 60 watt bulbs that aren't going to be giving off 60 watts.
They can't ever make more than 60 watts.
Well, it's right. The rating tells you beyond which power they'll burn out, or it's not safe to operate them. Yeah. Okay? So that's my general disclaimer. Now, so this year I can give you a question like, what is the current through a typical 60-watt bulb? And by typical, I'm telling you what?
Not.
Yes, which in America, typical means I'm operating it how?
Normal.
Yeah, plugged into a 120 volts. Now again, can I operate a 60-watt bulb at different types of power sources? Yes, but that doesn't interest us right now.
So why does it have to be 120 volt then?
Because in America, that's the voltage that your standard household outlet comes to you from.
So it doesn't
And-
have anything to do with the 60?
No,
Like,
has nothing to do with the
change it
60.
to like 80?
That's correct. And when we get into the electric power grid that services your home, we'll talk more specifically about why or how that works out. So what is 60 watts? That's a what? But what is 60 watts? What given information is that? That's power. And what's the unknown? I, current. So we have P equals IV is the relationship. Isolate the unknown and we get I equals P over V. Whoa. Therefore 60 divided by 120 gives me 0.5 amps. Now, what if I change this question and asked for a 100-watt bulb? Is the current going to be higher or lower? Higher. Because now this becomes 100. And I get 0.83 amps. And that doesn't surprise you, right? Because the higher power rating plugged into the same voltage would mean there has to be a higher current. But what if I asked you this? What if I said, what is the resistance of a typical 60-watt bulb? Well, I know that the voltage is 120. Power is 60 watts, but I'm looking for R.
We solve the current first and then you solve for R.
Okay, I could use P equals IV to solve for current first, and then use Ohm's law, V equals IR, to solve for resistance. But rather than do that, we're going to come up with a couple of shortcut equations. And all they are substitution equations. So for example, if I take P equals IV, and I substitute for V equals IR, then I get P equals what?
Squared R.
I squared R. Or I take P equals IV, and I substitute for I. What would I equal?
V over R.
V over R.
V squared over R.
So P equals V squared over R. So these two equations, well, it depends on what I'm given and what I'm looking for, right? These two equations are just shortcuts. You saw me do the algebra, right? They're just the definition of power, P equals IV, and Ohm's law, V equals IR, in algebra. But it will help me in a question like this, because now I know that if P equals V squared over R, I can solve for R directly with just P and V. So R equals V squared over P, which in this case would be 120 squared divided by 60, right? So it's 240 ohms. Yeah.
On our formula page, the last formula we have is 4.
Yes, we definitely need to update them.
What?
We will update them soon, today. All right? Actually, let's do it now. Sure, why not? No, I think you're good. I don't think you need any. I mean, the only one that's really carrying over, and you have it this way in your notes, is Newton's law of gravitation. So I think we're good. All right. So these are the new formulas on your formula sheet. Got Coulomb's law, right? And we know that the effective resistance of resistors in series is equal to the sum of the individual resistors. And the reciprocal of the sum of the parallel resistance of a group of resistors in parallel is equal to the sum of the reciprocals of the individual resistances.
If this test had been combined with light, I would have...
And then Ohm's law and electric power. Oh, and then one more. Resistance for any given current carrying wire or other conductor is resistivity times length divided by cross-sectional area. Yes, that's rho, resistivity. Alright, so those will be updated on your formula page. Alright, now, I'm also going to ask you a question like this. I'm going to say, going to ask something like this. How much does it cost to light a 60-watt bulb for 8 hours? Because I don't know if any of your parents are like this, but my mom would always charge me a quarter every time I left my light on in my room. And so when I got smart enough, educated enough to do the math, I wanted to know, am I getting ripped off? Right? And so, let's find out. If it is just a 60-watt bulb, and I leave it on all day for 8 hours, how much is that costing? Well, a typical rate, and by the way, it changes. It varies from place to place, and then it also depends on how much your usage is. Usually what the electric company will do is they'll charge you for a set number of kilowatt hours, a certain rate, and then once you go over that amount of energy, then they charge you a higher rate, right, to discourage you from using more than you need. But we're going to assume an average rate of 15 cents per kilowatt hour. And by the way, kilowatt hours. Let's break that down. Kilowatt is a measure of, it's 1,000 watts, and so it's a measure of power. And if I take a power and multiply it by an energy of, by a unit of time, I get what? Energy. So they're charging me for how much energy I use in a unit called kilowatt hours. So we just need to find out how much energy it takes, and then we can multiply that by 15 cents to get how much they're going to charge me. So, again, I know that the power is 60 watts. I know that the voltage is 120 volts. And I'm given a time here in hours. So, what do I do first? Excellent, I convert to kilowatts. I have 60 watts and I need it in kilowatts, and so I'm going to use my unit conversion technique here of 1,000 watts is the same as 1 kilowatt. So 60 watts is 0.06 kilowatts. Then I'm going to say energy is power times time. Well, the power is 0.06 kilowatts, and the time is 8 hours. Therefore, the energy is 0.48 kilowatt hours, right? And then this right here, this rate, is just another conversion factor. If I know that I have 0.48 kilowatt hours, this rate tells me that 1 kilowatt hour is what? Equal to 15 cents. So kilowatt hours cancel, and I get 0.48 times 15 cents is like 7 cents. So my mom's turning an 18-cent profit every time I leave it on, right? But of course, the point was I need to be responsible and turn it off. And you know, those 7 cents add up. Good question. What in your house uses the most energy?
Conventional ovens.
No. Refrigerator and
Some that's on all the time.
air conditioner.
How much?
Because they're working backwards. They're removing heat, and that's the hardest thing to do. So your air conditioning and your refrigerator are going to be the biggest drains. Next is going to be producing heat, which is your dryer, your electric dryer, and your oven. Well, producing heat through a resistor, electrical resistance. And those are going to be your other big drains. And everybody else, you know, your hair dryer, right, is also one that's producing heat through a resistor, so that's going to be a higher one than maybe some others. And then it goes down from there. Now, speaking of hair dryers, does anybody know what the name of their hair dryer? I mean, not like Susie, like you nicknamed it or something, but what's on the barrel?
Red Dot.
Well, all right. Your hair dryer might look something like this. Well, yeah, that's about the best hair dryer you'll see all day.
You don't have a handle.
You don't need a handle.
This is for people with really small hands. Why, thank you. And so let's see. What's the name of a brand of hair dryer? Does anybody know that much at least? Who? Revlon. So this one's called the Revlon 1650. What does this number represent? 1650 what?
What model numbers?
Watts.
What? Now you go find your hair dryer and figure out its resistance.
Exactly. I could find the resistance to that, right? I could find out how much they're going to charge me to run that hair dryer for, say, 10 minutes.
8 hours.
Let's say it takes me 10 minutes to dry my hair. How much are they going to charge me to dry my hair with the Revlon 1650
I don't know. We should do
for if it takes you 10 minutes?
We should do 1.65.
Figure it out. All right. So then the last thing I'm going to ask with power is, and again, we're simplifying, but your house is set up on a series of separate circuits. And you might have a 10 amp circuit breaker on a certain circuit. And again, when we get into electromagnetism, we'll talk about how the circuit breaker actually works. But for now, just know that what that means is if the current exceeds 10 amps, and again, we're simplifying, it doesn't automatically trip the second it goes over 10 amps, but anyways. But for our purposes, we're going to pretend it does. If it goes over 10 amps, then the circuit breaker trips and shuts off the power. You've ever had that happen in your house? You have to go to the breaker box and reset the circuit, right? So I might ask something like this. Can a 1650 watt hair dryer be used on the same circuit at the same time as a, I don't know, let's say mom's running the vacuum, 2400 watt vacuum.
Use wattages after.
Yes, these are very realistic. Actually, the 2400 watts is not. Oh, hold on a second. That's a little high. Let's make it 1800.
It'd be that much less. That'd be just that much more than the hair dryer?
Yeah.
I think a vacuum would be a lot.
If it's a 20 amp circuit. Now, a couple of different approaches. I can determine the maximum power that can be run on a 20 amp circuit and compare that to the amount of power I'm trying to run. Or I can take these power ratings and find out how much current each of them will use on a typical circuit, and then add them together and compare it to the 20 amps. Either way, I get the same answer. Which way do you want to do? Do the first one? Okay. If P equals IV, then the maximum power on a 120 volt circuit and a 20 amp circuit is 20 times 120, which is 2400. But if I add 1800 and 1650, I get 3450, which is higher. And so that would trip that breaker. Salud. Yes, so the answer is no, they cannot be used at the same time on this particular circuit. And then I might say something like, little Johnny, he's a bit of a troublemaker. He turns on his sister's 800 watt curling iron.
I can tell. Not really.
Yeah.
Definitely everybody is I don't want people on the internet to hear my vision. JT.
What's that?
I have too many.
Jordan Truitt. He can do it. Phone number.
Nope.
It starts turning on. Start turning on 60 watt bulbs on the same 20 amp circuit. Oh, that's not a question. How many bulbs can he light before tripping the breaker? Before tripping the breaker.
Yeah.
So again, we can do one of two approaches. We can find out the maximum power and compare, or we can find the current and compare. Which do you want to do? Do the current this time? All right. So what current does the 800 watt curling iron use? P equals IV, then I equals P over V, which is 800 divided by 120. 6.5, or what is it? 6 point who? 6.6. And then a 60 watt bulb is how many amps? I mean, how many amps? We did that earlier, right? It's 0.5 amps. So he's got 20 minus 6.6. He's got 13.4 amps left to play with, right, before he trips the breaker. And so at half an amp each, he can turn on 26 or 27.
Well, 27 break it.
Right, the 27th trips it, right? So he can turn 26 bulbs on before tripping it. If he has 13.4 amps, and I could do it this way, right? 13.4 amps, and one bulb is 0.5 amps, and so I get the 26.8 bulbs, but I can't turn on an eighth of a bulb, and so the 26 is safe. Okay? Questions?